Raw processing power creates a convincing illusion. When a program executes instantly, it is easy to assume the underlying logic is highly efficient. But physical time is an unreliable metric. Imagine deploying the exact same block of code across two drastically different physical machines. Computer A is a modern cluster, processing 1 billion operations per second. Computer B is a standard localized machine, maxing out at 100 million. The code is identical, yet Computer A will finish 10 times faster. If the exact same sequence of instructions yields two completely different physical execution times, then seconds and milliseconds are invalid metrics for measuring the true quality of the algorithm itself. To accurately evaluate efficiency, we have to discard the clock entirely. Instead, we must count the absolute number of fundamental computational operations the algorithm executes. This gives us time complexity, the measure of how these basic operations grows strictly as a function of the input size. We define that input size using a universal mathematical standard, the variable n. To find objective truth in computer science, we must completely divorce our analysis from physical hardware. The mathematics must stand on their own. Stripping away the physical machine leaves us with the abstract architecture of raw code syntax. Consider a simple, isolated command to print a word to a screen. Whether your underlying dataset has 10 items or 10 trillion, this execution footprint does not change. Because its execution is entirely independent of the input size, we define this as constant time, denoted as O of 1. Now observe what happens when we introduce iterative scaling. We wrap a similar print statement inside a standard for loop from 1 to n. The basic operation now executes exactly n times. If the dataset doubles, the required operations double, creating a direct scaling relationship known as linear time. The computational load compounds drastically when we introduce dimensional scaling through independent nested loops. If we place a second loop inside the first, the inner loop must execute its complete sequence of n operations for every single iteration of the outer loop. This creates a strict multiplication effect. The algorithm's total runtime now expands at a quadratic growth rate, calculated as n squared. By applying this structural analysis, we can mathematically predict the processing load of complex algorithms before the code is ever compiled. However, the raw size of the input is not the only variable. The physical arrangement of the data firmly alters the algorithm's trajectory. To test this variability, we will run a standard linear search algorithm across this array of 5 integers. Every algorithm has a best-case scenario, the absolute minimum time required under the most favorable conditions. If we search for the number 10, it finds the target immediately on the first check, requiring exactly one comparison, yielding an O1 efficiency. Conversely, the worst-case scenario guarantees absolute maximum time when the target is at the very end. Searching for 50 forces the algorithm to check every single element in sequence, requiring n comparisons and scaling linearly. Real-world applications rarely hit exact extremes. To assess everyday reliability, we require an average case analysis. The average case calculates expected runtime across all possible inputs. Summing the required comparisons for every successful search and dividing by the total elements yields an average of 3 comparisons, generalizing mathematically to n plus 1 divided by 2. In complexity analysis, constants and divisors become mathematically irrelevant at an infinite scale. We drop them from our formula, leaving the average case at O of n. An algorithm does not operate at a single static speed. It exists within a spectrum of probabilistic bounds, dictated by the shape of its data. Basic visual counting works well for isolated logic blocks, but it fails when loop boundaries are dynamic. Take a dependent nested loop. Notice the inner loop's limit is not fixed. It is strictly bounded by the current iteration of the outer loop, I. Because of this dependency, we cannot simply multiply n by n. We must map the execution footprint step by step. On the first iteration, I is 1, yielding a single execution. When I is 2, we get 2 executions. The third iteration yields 3, and so on. This physical, geometric staircase pattern mirrors a formal arithmetic progression series. By adding these steps, we are simply finding the sum of the first n natural numbers. In discrete mathematics, this progression resolves into a standard formula, n times n plus 1 divided by 2. Expanding this binomial equation leaves us with two distinct polynomial terms, n squared plus n, all over 2. Applying the core axiom of asymptotic analysis, as n scales toward infinity, only the highest order dominant term dictates the mathematical trajectory. We strip away the lower order n and the divisor, isolating the dominant term. The final complexity for this dependent loop is strictly quadratic. We have successfully translated raw programming syntax into a mathematical model, proving that all structural logic is ultimately reducible to pure mathematical series. These isolated formulas are highly theoretical. They are only useful when pitted against one another on a unified scale. This chart graphs the total processing operations required against a constantly increasing input size, n. We plot the highly efficient curves first, the completely flat baseline of constant time, followed by the steady, predictable diagonal climb of linear time. Contrast those with the aggressive upward trajectory of quadratic time, where the processing load compounds with every new piece of data. But quadratic scale is entirely manageable when compared against the extreme limits of inefficiency, exponential and factorial time complexities. These mathematical bounds scale so aggressively that they rapidly become computationally impossible for physical machines to process, even at relatively small input sizes. Minimizing mathematical growth rate is the only guarantee of operational supremacy at an infinite scale. We have established how to count operations and map probabilistic bounds. Now, we must formalize the strict mathematical language used to lock these limits into place, the asymptotic notations of big O, big omega, and big theta.